Got started with the recording. So here we have the center of gravity or the center of mass. The definition of these 2 points can be slightly different depending upon what we are trying to talk about, and why might we require to talk about 2 different terms which are practically the same thing. I'm going to talk about that in a bit as well. Have a look at the definitions. The point through which the weight of an object works is the COG. COG stands for center of gravity, whereas the center of mass is defined as the point where all the mass of an object can be considered to be concentrated, is COM. Uh, the idea of considered to be concentrated can be elaborated something like this: that if we have all the mass and if we squeeze up the entire mass of the whole thing into one single point, hypothetically, it is physically impossible for our real world, but well, might be a possibility for the black hole, but we don't know it, know yet, because they are unobservable. But that's our best guess. But for regular world, it's impossible to squeeze something into a point, uh, because that would give us infinite density. Irrespective of that, if we squeeze up a certain object to such a point that we squeeze all the mass into one single point, that location where all the mass can be considered to be concentrated is what we call the center of mass. Now, any object center of mass or center of gravity is practically the same point. It is absolutely the same point. Location wise, there is no difference, or practical purpose wise, there is no difference either. The reason we have 2 different names is this: that we can only use the term center of gravity whenever any mass is under the effect of a gravitational field. So if an object is not under the effect of a gravitational field, for example, let's say if we send a spaceship into space, deep space, where it's not orbiting around any specific star or planet, it is just traveling through the vast emptiness of space. For a situation like this, you cannot use the term that of gravity, because if the object is not under the effect of gravity of any object, then the idea of center of gravity actually does not stand up. However, the idea of center of mass is a ever applicable term that we can use everywhere, because any object is always made up with mass, and the center of point of that mass is what we call the center of mass. So that works out pretty well for us. So if we go further, both are actually the same point. Geometric objects have their COGs at geometric center. Now, geometric centers, there are multiple ways to find the geometric center. I'm going to talk about that. How can we find out the geometric center of different objects over here? For a circle, the center of a circle is a geometric center. Any object that somehow depicts like a circle. For example, if you have a ring, the center of a ring would be the center of that ring. Now, it is important that you need to understand that the center of gravity of an object does not have to be embedded inside the mass of the object. For example, if you think for a hollow object like a ring, its center of gravity is actually at the center of the hollow space of the inside ring. So it is a spatial point which is not located inside the actual mass of the object. Similarly, if you consider a pipe, a cylindrical pipe, the center of a cylindrical pipe is at the floating point, or is at the midpoint of the center joining line of the 2 opposite faces. So we have some figures over here. You might as well see that. Okay, let's go ahead. This is a circle. If you have a parallelogram, you draw the diagonals, you get the center of gravity. If we have a triangle, any shaped triangle, not essentially an equilateral, this one apparently looks like an equilateral, but any shape of triangle, it can be a scalene triangle. If we draw the 3 medians, if you draw the 3 medians of the triangle, medians means the lines joined from one of the vertices to the midpoint of the opposite side. So this is one of the vertex, and this is the opposite side. If we draw a vertical line up through here, this is one of the median, this is another median, this is another median. So these 3 medians will always pass through one single point, and that is concentric, that concurrent point through which all the medians will pass through is defined as the center of gravity of a triangular object. To be honest, this is basically the mechanism by which we can find out, this one is the practical mechanism by which we can find out the center of gravity for any unknown object. We're going to talk about that after a while. Just bear with me. Then if we go for these two are this was a linear object. These two are surfaces. Then we go for three-dimensional object which has two dimension. So this is a full sphere, solid sphere. Center is at the center. To make it look like a sphere, we have given this flat type of line so that you can see it as a three-dimensional object. Because other than this this additional line, this the drawing of a circle and a sphere would pretty much be the same. Then we can consider the cylinder. If it can be a hollow cylinder, it can be a solid cylinder, but the center of gravity for a cylinder is always the midpoint of the line that joins the center of the two opposite faces. And then we can have a donut-ish type of structure. This is something I call the ring, or it can be a toroid as well. A toroid means if we have a ring-shaped pipe. So it's a pipe that is shaped in a ring. So that's why it was written as donut-ish, where the center of gravity is pretty much at the center. So these are geometric objects or which have a certain sort of symmetry within them, for which we can find out the center of gravity with practical geometric methods. There is not so much hardship in finding these things. However, if we have an uneven object, then we can find out the center of gravity in a different mechanism. That experiment will be described in a while. I think this experiment comes up right here. So we'll talk about this. But let's have a look at this paragraph. Physical significance of center of gravity or center of mass is that if we assume to divide the object into two pieces and cut through the center of gravity or center of mass along any direction, then the two sides will be of equal mass. So an object can be balanced by applying force directly to or from pivot point that is equal to weight and works upwards. Let me elaborate what this essentially means. Let me draw up in my paint. Let me draw up a triangle of any random shape. Can I draw a triangle of any random shape? I think not. I can only draw isosceles. Okay, let me draw an isosceles maybe. Okay, this is an isosceles triangle. Almost looks like an equilateral, but let's say this is an isosceles. I know this for a fact, this is an isosceles. Now, if I find out that if I draw the individual medians with, let's say, red, using a thin line, let's say this is the midpoint vertically down. So let's say this is the midpoint. So, okay. So this is one of the median, approximately vertical midpoint median, okay. And then another one maybe drawn like that, let's say about this much. I'm not really sure, I'm just eyeballing it. So whenever I have drawn two medians, I can pretty much be sure that this should be the COG point of this triangular object. Let me maybe mark it with a bit of green to make better sense. Okay, now to make sure that this is the correct point, I can go ahead and try the third. I don't need the crossing of all the 3 points to find out the single point, because you can essentially get a single point by simply, what is this? Okay, I did something over here. Never mind. So I can essentially we can find out the location of a single point by crossing two lines. If two lines cross each other, that cross point can define a very specific point. You don't need 3 lines to go through the same point to find out one single point. One single point can be found out by crossing 2 different lines. So we can find out the position of center of gravity by simply joining the two medians. However, just to make sure that what we found over here is correct, we can definitely try and draw the third line. And if we did the earlier 2 lines properly, then this third line must also go through the center of gravity point as well. Now, I can go ahead and show you the geometric proof for the next part of the drawing, which was labeled over here. But I am not interested. But if you want to, I can show you in the messenger maybe. I'm not going to show you the geometric proof right now. For geometric proof for this part, have a look. For any direction, if you consider the vertical height for the triangle from any of the side to the opposite vertex, the position from the center of gravity will always be 1/3 of the total vertical height. This is a generally acceptable property, general property for the median point of a triangular shaped object. The COG will always be 1/3 of the total height above, which means if you consider this vertical line, this median point divides this line into 2:1 ratio. So the top is double, the bottom is 1. So 2:1 ratio means if this is h, this is 1/3, and this remaining part, which is not labeled over here where I'm hovering my mouse, this point would be how much? Etu কতটুকু হবে? 2/3 of
2/3 of the height.
2/3 of the height. So vertical height, that is. So that's the property for the center of gravity. And so what does this paragraph means? This paragraph means that, let's say this is a triangular piece of object, metal sheet or cardboard paper, or maybe a piece of any flat object that we can work with. And let's say we have found out this is the center of gravity. The significance of the center of gravity is that if we now cut this object through this center of gravity along any direction, not essentially through these red lines. We use these red lines to find out where this is located. Let's say if I want to cut this object, I'm using, let's say, dark blue and using a slicing line. If I want to, let's say, cut this object through this alignment, then the total mass of this left side of this blue line and the total mass on the right side would be exactly equal. If I change the orientation of this line, maybe let's say I'm gonna cut this line, cut this object along this orientation, some random orientation like this. In this case also, the total mass, let me just label this for you so that you can understand what I'm trying to mean better. So the total mass of this side, the left side of the blue segment, this quadrilateral, the mass of this part would be exactly equal to the mass of this part. এখান থেকে শুরু করে and all the other parts. So if we cut any object through the center of gravity into two pieces, the two pieces on the two sides of the cutting surface cutting line will always have exactly equal mass. This gives us a good idea that this would be the perfect balance point for that object to be balanced, which means if we now want to support this object, we can simply put one single finger under this point, and if we just can keep our finger exactly at this point and support it by a single point, this object will be perfectly balanced. This will not roll over or tip over. This will be perfectly horizontal. It can be maintained horizontal by giving a single point support over here. Similarly, if we make a hole over here and put a string through here and let's say attach the string with a bigger object, let's say a piece of coin or some piece of stone, and hang the object from this point, so that this thing eventually looks something like this. So this is the hanging point. We're hanging it from the center. If we hang it exactly from the center of gravity, this object will be perfectly horizontal. Being horizontal means it is equally balanced on all sides by, if you consider it divided into two pieces, left or right, top or bottom. So any alignment of cutting will always make the object to get two equal mass pieces. That's why the object is perfectly horizontal, because if it was not equal on all sides, I mean bisymmetrically equal on all sides in terms of mass, then the part that is heavier would definitely tilt down. So that's a very important significance. Another interesting significance for the center of gravity or center of the mass of an object is that let's say this is a triangular object and we are looking it from the top. So this is the top view of the object. So I'm going to show you some additional drawing over here. Might as well use a bit thicker line and use a different color, maybe brown. Is that we can, if we want this object to be balanced, by providing support underneath it. Underneath means we're going to support it on top of something. For example, like the legs of a table. The legs of the table stay below the surface of a table. So that's a equilibrium scenario where supports are provided from under. Objects is placed above the supports. Another type of balancing can be done where the support is placed above the object and the object is hanging from a point. For example, the ceiling fans. Ceiling fans always are hanged from a single rod. Have you kids ever seen any ceiling fan that hangs with more than one rod? Anyone ever? Hello. Every ceiling fan is always hanged by a single point. There's a reason for this. The reason is that if we hang an object directly from its center of gravity, we do not need to have multiple different support lines. One single support directly working to the center of gravity can make an object perfectly horizontal, and it is good enough and it is stable. It's not gonna roll or tip or bend on one side as long as that rod is placed exactly above the center of gravity. It's perfectly good. But you kids might have never seen a single point supported chair or single point supported table, because this is pretty difficult to make. We are going to have a certain surface area of that object, of the support system. We might have seen that we can have objects which have a single point support system. For example, table fans, typical table fans, they come with a single support system, and then there is a motor and the fan rotates by. So that's the object supported by a single shaft, but that shaft actually sits onto a rectangular piece of board on which there are switches. So that rectangular piece practically works as the base of the object. So it's not essentially the support may be a singular rod which goes up in a conical shape, but actually the base is a rectangular surface on which the whole fan is placed. Yeah, some of you have raised hands. I'll give you floor to ask questions. Just give me a little while to finish up this discussion, then I'll take questions. Now, important part that I want you to understand is that if you're trying to support an object from underneath, to have stable support system, we need at least 3 points. At least 3 points. Achha. If you wonder that why do you need 3 points? Well, let me elaborate this thing for you. Let me choose a much thicker line to make sense with it. If we place a single point, a very sharp edge of a pointed tip under this exact point, center of gravity, we can essentially make the object stable. But this would be a stable that is very willing to become unstable. I mean, you move the support system a little bit, it will try to roll over, and eventually it will flip over to the any of the side. It will not be very stable as you want it to be stable. So that's about the point support. The other thing that we can do is that underneath this surface, so what I'm about to draw right now with brown, this will mean that there's a place under the surface. Let's say under the surface, we can give a line that maybe goes along this line, thicker lines. Okay. Let's say we are going to give a support, or maybe a piece of cardboard, or maybe a piece of wood, where the wood is going to go to the center of gravity. If we can place a linear support, one line support, underneath the object that goes to the center of gravity, this object can be also kept into balanced. This object will be balanced. This, because of the support system, this will not fall on this side, but because there are only one single line, it can very easily roll about this line. So it means that this object can fall if there is a bit of a vibration, or if someone actually pushes this end a little bit, then it might fall onto the right side, or it might fall onto the left side. It means that if the falling starts on one side, then you cannot stop it, because it's going to keep rotating because of the rotational inertia of the object, and eventually the object is going to fall onto their side. This gives us a bit of stability, additional stability, but this is not perfectly stable either. Here, if you wonder that other than having a single line of support, we can also achieve this same thing, this exact similar thing. If we place two supports, let's say exactly on two opposite side of this object. For example, let's say if you use two fingers, two of your fingers. Let me show you those position of those two fingers by drawing dots, maybe. Okay. So let's say you put one of your finger right here, and by trial and error, you place your other finger in a position such that, on the other side, in a position such that, if we try to imagine a straight line, that will essentially go through the center of gravity. If we try to imagine a straight line, so this line is not available. These are two of your fingers, and there is nothing in your fingers. But if you can place your fingers or two different support points in such a way that those 2 points essentially go through the center of gravity, you can also make this object quite stable. But it will not be very stable, because it can still fall on the left or the right side, because this is only supported by 2 points. However, actually, what I want to say is that if we want to give the object a proper stability, we need a minimum of 3 support points. Let's say this is one of our support points that we're going to work with. So how we can make the object stable? To make the object stable, if we want to make this object stable that is not going to fall over, we need to give at least 3 support points. These 3 support points has to be located in a way that they should form a triangle in such a way that the center of gravity of the object should be located inside that triangle. Let's say I'm representing these 3 brown spots as a possible location for 3 support points. Now try to visualize a triangle made by these 3 points. So if I go ahead and draw, let's try to visualize this triangle. That what triangle does these 3 support points make? So this is one line, this is another line, and maybe this is another line. So you can see this is the triangle that these 3 support points make. Does our COG belong inside this triangle? The answer is yes. If this is achievable, then this object can be perfectly stable onto this object. But if it is not achieved, let's say by misplacing it or by wrong positioning, we're gonna do something messy. For example, let's say we place 2 of our supports here as shown, one over here and one over here, and let's say the third support is placed right over here, maybe here. The third support is placed over here. Now if I try to make a triangle over here, try to visualize, this triangle will not essentially go to the center of gravity, or the center of gravity will belong outside this triangle, which means this support system cannot make the object stable, because now the center of gravity is falling onto the other side. So this object is going to roll about this line. This is going to be our roll. So it's going to get off from this support point and it's going to roll onto the right side and it's going to fall over. To make the object stable, we have to give 3 different support points at least, so that the center of gravity is located in the imaginary triangle made by those 3 support points. Other than that, we cannot make the object perfectly stable. So this is one of the requirements for a stable object. So any object can be made stable by giving bottom supports or supports below it, where we need at least 3 supports. This is why in chemistry labs you have seen that we have tripods, because 3 support points make a certain object stationary enough, and you could have enough gap on the 3 sides so that you can put the Bunsen burner or other stuffs underneath the flask or anything whatever you place on the tripod. And if you wonder, then why do we make our tables and other stuffs to have 4 legs? The reason we make 4 legs, one of the main reasons that we make 4 legs, that we human beings are really used to the idea of squares. If you wonder why, because we've been fascinated by the idea of 90 degree, and we are comfortable with things being square. And on a square thing, a square table could be very well adjusted by placing 3 legs at 3 different points, and this table would be stationary and stable. But for the idea of symmetry and also for equal load bearing capability, so that it has equal loads on all the sides, we prefer to have 4 legs on the 4 corners other than having 3 legs. So whenever in place of 3 legs, if you give 4 legs, each of the leg would bear a smaller portion of the weight. For example, if the weight of the table is, let's say, 1000 Newton, and you place the 3 legs at equal separation, each of the leg mathematically would take about 1/3 of that 1000 Newton weight. So that's a 333.33 Newton weight. But if you give 4 legs, if they all equally share the load of the weight of the table, they're going to be getting 250 Newton. So whenever you have a smaller load, you can design your support system to be thinner, and they can be more sleek and more last longer. And obviously we have the added advantage of looking it to be symmetric, which we human beings are very comfortable to, and what we desire from our natural tendencies. I don't know how, somehow it got embedded within our genome by evolution, whatever. And we like to have symmetric things. So that's the idea for how stability can be achieved. Okay, I'll take questions. Nuhan, you raised your hand first. Go ahead. Hello.
Ji sir.
Yeah, you have a question?
স্যার একটু অ্যানোটেশন দিয়ে দেখাচ্ছি।
No, sure. Annotation to allow করা আছে, I believe. I did not stop the annotation. Yeah.
স্যার লাইনটা এরকম হতে পারে না, আমরা কেমনে বুঝবো যে এই লাইনটা এদিকে হবে না? আমরা তো এদিকেও দিতে পারি, আবার আপনি যেখানে দিয়েছেন সেটাতেও দিতে পারি। আমরা এখন কেমনে বুঝবো যে কোন দিকে দিলে সেন্টার?
Which line did you draw?
ব্লু লাইন।
This one?
ইয়েস স্যার।
Acha, beautiful. Now I see it. You are proposing this line for what purpose? To find out the COG or to support the table?
সেন্টার অফ ম্যাথ।
To find out the center of mass.
জি স্যার।
Now, the geometric way to find out the center of mass for a triangular object is to join the vertex with the midpoint of the opposite side. So using some string or using some meter rule, we're gonna find out the exact midpoint of this line. I eyeball this point, or eyeball means I just assume this point is over here. I did not measure it. So, but in practical experiments, we're gonna measure how long is this. We're gonna mark up the exact midpoint of this thing. Then we are gonna join from this vertex up to that midpoint to find out this median line. So this can be over here, this might as well be over here because I did not actually measure where this midpoint is supposed to be. So all of these 3 lines are called the medians, which means they are the lines adjoining one of the vertex to the opposite side's midpoint. So geometrically this will be a fixed line. There is no multiple options for this line because you're going to get one fixed midpoint for a specific side of a triangle. বুঝে গেছে?
বুঝছি স্যার, বুঝছি।
আচ্ছা,
মানে আমি যেখানেই দিই সেন্টারটা সেম থাকবে।
হ্যাঁ, তোমার ট্রায়াঙ্গেলের শেপ যেরকমই হোক না কেন, সেন্টার অফ গ্র্যাভিটি পজিশন ওইখানেই থাকবে।
ওকে স্যার।
Center of gravity, মানে if you change the shape of the triangle, height of the triangle, your midpoint, your triangle side would also change their lengths, but it will always keep that proportion, that this 1/3 thing that I just showed you over here, this proportion would always be intact. বুঝে গেছে?
জি স্যার, বুঝেছি।
Yes, Monuddin, go ahead.
স্যার, আমরা যদি একটা ট্রায়াঙ্গুলার অবজেক্টের নিচে একটা সার্কুলার সাপোর্ট দিই স্যার, কমপ্লিট সার্কেল স্যার, তাহলে স্যার ওই দুইটা সেন্টার অফ গ্র্যাভিটি কি ম্যাচ করতে হবে ইন অর্ডার টু বি ব্যালেন্স?
Not essentially. Not essentially. Whether it's a hollow circle or it's a solid circle, you just have to make sure that the center of gravity of this table, center of gravity of this table, let's say tabletop, this point is somewhere on that circle. That way you can keep it stationary. It's not going to fall over. So for example, let's say if I try and draw that, let's say I draw this one and fill with a solid color of the same color. Can I not fill this? Okay, and I'm gonna transparent selection this. So let's say this is my solid support. I can place this support over here or here or here or here. As long as my center of gravity is falling within this circle, my table would be stationary. It would have the tendency to fall over, but it would not fall over like a line or like a single dot. It can still take some amount of vibration or forces. It would still be stationary. But if you place it somewhere over here, then it will necessarily fall over on the other side. It doesn't exactly have to match at the center. However, if it matches exactly at the center, you would have the highest stability. বুঝছো কি বলছি?
Yes sir.
The further you offset from the center to center, it will become more unstable. It will be more prone to fall over to the side which is heavier. In this case, this side is heavier, this side is less heavier. But the better you can match the center to center, it will be more stationary, more stable. বুঝে গেছে?
Yes sir. So that means ওদের যদি সেন্টার অফ গ্র্যাভিটিটা ম্যাচ করে তাহলে ওরা পুরা স্টেবল হবে, একদম কমপ্লিটলি স্টেবল। That is the basic thing.
I wouldn't say completely stable because let me elaborate why I am slightly disagreeing with you.
Okay.
If I want to define an object to be completely stable, this would mean that nothing in the universe can topple that object over. Like nothing can roll over that object, but that's not essentially true. What we can say in a comparative sense, that more stable or less stable, if I could match these two, for these two apparatus setup, this would be the most stable they could get. I mean, using a circular support of this much diameter and a triangular object of this size, if you match up the center of mass and center of mass perfectly, for example, I attempted over here, not precise, but I attempted. So you would get the most stability possible to get out of the interaction of these two things. And the further you move from this orientation, the less stable it is gonna be. If this circle is located outside the center of gravity, it will be naturally unstable and the tabletop is simply gonna fall over. For example,
Yes.
I mean, I wouldn't say something to be completely stable because there is no such thing as completely stable. Using enough force, you can roll over, topple over, flip over, anything and everything. Now, whenever I say using enough force, this could mean there is no upper limit. Do I make sense?
Yes, sir.
Beautiful. So choice of words can make quite a difference. So over the time, to me, should we use most? Should we use more? I mean, is it a comparative degree make more sense, or should we go for the superlative? Like it's a stable object. Full stop. It means what? That it's a ever stable object. I mean, is this possible to achieve? Normally, no. That's what I meant. Yep. Any other question? মাঝখানে আরেকটা কে যেন হাত উঠাইছিলা পর আবার হাত নামায় ফেলছো, but did I get your question answered?
Sir, it was me. It was me.
আচ্ছা ঠিক আছে, beautiful. So this was the idea for the stability. So I'm going to go to this paragraph one more time and have a read at this paragraph and see if it properly makes sense. আমি কতদিন পোলাপান থেকে ট্রিট দেই না,
জি স্যার।
আমার 3টা ব্যাচ আমার কাছে ট্রিট পাওনা আছে। কোভিড এসে সব পার করে ফেলছে। I hope there is no question.
না স্যার নাই।
We're gonna go for this experiment. This is a very pretty simple experiment. I would like you to read this experiment. এটা পুরোটা পড়ো and then try to see this figure, and then I'll take questions and then I'll answer the other parts. Read it through. তোমাদের কাছে প্রিন্ট আউট আছে, প্রিন্ট আউট থেকেও পড়তে পারো, be my guest, whatever you want. I'll give you 3 minutes to finish this reading. 27.
স্যার এটাই আমার প্রবলেম।
হ্যাঁ পড়ো, আমি
বুঝি না স্যার।
ডোন্ট ওয়ারি, আগে পড়তে বলছি পড়ো, go through the material, I'll explain, don't worry. So the way this thing is attempted is pretty simple. I'm going to explain what is happening. The point that I want you to understand that if we hang an object from a single point support and allow it to come to its own stability, it will always come to a position such that the center of gravity will be vertically below this position. If you wonder why, we can look at some figure from your federal book. Let me just find out some figure. So this is actually a good figure. I was trying to find out the position where it does not align, and I could actually show you the possibility of rotation. Okay. No. That's it.
স্যার আপনার স্ক্রিন ব্ল্যাঙ্ক হয়ে গেছে।
Sorry. I cannot find the figure that I'm looking for, so I'm gonna draw it anyway. But to draw this, I'm gonna require Paint 3D. So আচ্ছা, এটা এখানে থাকুক, ব্যাপার না। I'm gonna zoom in a little bit. How can I move this? There is a horizontal bar. I can, আচ্ছা let me just try to draw. মনে করো, let's say this is a non-uniform lamina. This is how a non-uniform lamina looks like. Okay, so এটা মনে করো একটা non-uniform lamina. Just for the sake of experiment, let's assume that its center of gravity is located at this point. This is the center of gravity point. এখন যদি এরকম হয় যে what I'm gonna do, we're gonna make a small tiny hole at one of the edge, small tiny hole, and make a pin go through it, and we're gonna hang this object from this pin. One of the important part is that this hole is gonna be quite small, so that it does not change the overall mass of the object very much, but the pin has to be small enough so that the pin is not stuck onto this hole, which means this object should be able to rotate freely. This object should be able to rotate freely whenever we hang it from there. It should not get stuck, like not like a screw or nut bolt. It should be able to hang free. So the diameter of the pin should be somewhat smaller than the diameter of this hole. Maybe the pin is of this much size, so the hole should be somewhat bigger. Now here's it. Let's say if we hang it over here, and this is a certain orientation of the object. This is the part that I want you to understand. The weight of the object is going to definitely work. Where is straight line? The weight of the object is going to work vertically down from the center of gravity. So this is the alignment through which the object's weight is going to work. So this is the object's weight. So let me mark that with a downward arrow. So let's say this is the weight working line, and this is your pivot point. So there will be a moment available. So how much is that moment? To find out the moment, we have to draw a perpendicular line from the pivot point onto the weight. I do the weight from here, so I cannot essentially draw a perpendicular line. Just for the sake of drawing, I can try to extend this line a bit backwards. Maybe I extend this line a bit backwards like that. And then if I draw a perpendicular line over here, this is my perpendicular distance, D. So this is my weight. Let's say this is my D. So currently this whole object is going to rotate about this support point or the hanging point in an anti-clockwise direction. So it's going to rotate a bit onto the anti-clockwise direction. The opposite thing can happen if we place the whole thing the other way around. So it means that if the center of gravity was on the right side below the hanging point, then it would have rotated clockwise. The only position where this whole thing can come to a complete rest can be, let me copy this. I cannot copy this. Control C, Control V. Could I copy this? Okay, yeah. The only way this whole thing can come to a perfect stationary orientation if the object comes to this orientation. Now I am approximately drawing this orientation. To show you this orientation, it means that now the weight is not going to work in this alignment, so I might as well erase that weight, because now the weight will always work vertically downwards. And if the center of gravity for is still located right up over here, if this is the position of the center of gravity, the weight is now working vertically downwards. So this is the weight working line. This is the W. And when the weight is vertically below this hanging point, exactly on the same alignment, then the moment will become zero. This is the only position where the object can come to rest while it is allowed to rotate freely. And whenever it will come to rest in this orientation, we're going to hang a plumb line from this same pin. A plumb line, এটার ভালো একটা ফিগার আছে, সাইড ভিউ আছে। তোমাদের ফেডারেলের বইটা একটু হাতে নাও, ফেডারেলের বই থেকে তোমাদের একটা ফিগার ডিরেক্ট করে, তাহলে আমরা বুঝাতে সুবিধা হবে। এক মিনিট। আমার বই। Go ahead. So we turn up to the federal book at page number বুড়ুর বুড়ুর শব্দ দিচ্ছে মেসেঞ্জার থেকে মোমেন্ট চ্যাপ্টার এটা কোথায় জানি আছে turning effect forces. This experiment is on page number 72. Turn over your federal book on page number 72. Everyone there? Paiso?
What book?
জি স্যার
ওই যে ফেডারেল বুক চার্লস চিউ লিয়ং সি চেং চো সি ফুং physics a course for O level second edition, the green
Which
cover.
page?
Huh?
Which page?
Page number 72.
Okay, thank you.
The typical Cambridge book that you are required to study. It was earlier published only from federal publication. Now it is also published from Marshall Cavendish. So the writers are all Chinese. So in Bangladesh, we don't usually use their names. But yeah. So if you go on to page number 72, which I believe every one of you are at, there you see that there are two figures. Figure 5.19 shows you the side view of the apparatus setup, and figure 5.20 shows you the face or the front view of the apparatus setup. So we are going to hang a plumb line. A plumb line is basically a thin piece of string and a heavy mass joined at the bottom. The property of a plumb line is that if you allow a plumb line to come to stable, or it does not oscillate or move or bounce or whatever, it is completely stationary, then that string would give you a perfect vertical line with respect to the earth, because it's being worked upon by gravity. So we're going to do that, and you can see it very well. The way we have hold the plumb line over here, this plumb line is not touching your object. Take a good look at the apparatus setup. They take a good understanding for the spacing. You can see that the object, the lamina, which is a bit colored thing, that is hanged by the thin pin, and there is a bit of gap between the end of the clamp and that hanging point. The lamina is not making any friction with the clamp, or it is not even touching the string of the plumb line. There has to be enough gap so there is no friction, so that the lamina can find its own vertical orientation without any unnecessary friction. So we're going to do that. And whenever everything comes to stationary, then we know that somewhere vertically below, somewhere, we do not know yet exactly, but somewhere vertically below this hanging point of the pin. So what I mean is somewhere along this line, you have to understand that I assume this position of center of gravity, but actually we don't know. We're trying to find this out. But when the lamina has come to a stationary condition, we can pretty much know, we pretty much perfectly understand that this center of gravity of this object would be somewhere below this hanging point. Now, anywhere below this hanging point. To find that out, what we're going to do, we're going to draw a vertical line through along that plumb line onto the lamina. So we can hold up, we can touch them after they come to stationary. We can carefully touch the string and the lamina together, and using a ruler, we're going to draw a vertical line along that string onto the lamina. This is going to be our first line. Then we're going to repeat this same experiment with another hole, which should not be too close to the object. So if our first hole is located here, we should preferably label our second hole pretty far apart, maybe somewhere over here. I mean, not really close over here or not really close over here. I'll tell you why we shouldn't preferably have it pretty close in a while. But just take my word, we're going to make a hole pretty far away from the object, and then we're going to repeat the whole process once again for this second hole. So this second hole should give us a straight line that goes, let's say maybe along this line. It's a bit difficult for me to draw a straight line like this, and we're going to get a straight line like that. These two straight lines would cross at a certain point, and this crossing point is essentially our center of gravity of that non-uniform lamina. So this is the basic experiment. To find out the center of gravity of the lamina, it is good enough to work with only two different holes and finding out the center crossing of two lines and finding out the center of gravity. Having two lines is always good enough. Just to make sure that what we did find out over here is absolutely correct, we can attempt this whole experiment using a third point. This is not essential to find out this thing. This is just for a proofing way that what we did over here is correct. If our experiment was good all through, we should find out that the vertical line that we might draw from the third point will also go through that same crossing point. which ensures that our experiment is correct. So in this figure, you can see that they are showing you that this experiment was done using 3 holes, but to find out the COG, we only need 2 holes. To confirm that what we found out from the for using the 2 holes, we can have a 3rd hole, but having the 3rd hole is optional, not essential for finding out. বুঝা আছে কি বলতেছি?
Sir, third point necessary to draw.
বুঝি নাই।
Third point is necessary to draw. Third line.
No, you don't have to draw it. For example, in this case, whether they have drawn it or not, I cannot say this because the string is above their lamina. But what you can see over here, that the 2 lines that you did draw from the first 2 holes, the 3rd line is essentially going through that exact cross point. You can see that there is a perfect coalescence. So if you can see that it is actually going through that exact cross point of the first 2 lines, you don't have to essentially draw this 3rd point, because the whole point of having the 3rd line or 3rd hole is to check whether what we find out is correct or not. If it goes to that same point, you know your experiment was perfect and you don't essentially have to draw that. But if you want, you can also draw that and have a foolproof version. I mean, drawing that line is optional. Drawing the 3rd hole is also optional, but it is a good thing to do just to make sure that the experiment was performed properly. Yes, 2 of our students did raise hand. Nuhan, you just asked your question. Nuran, yes, go ahead.
Sir, if the 3rd line isn't concurrent with the other 2 lines, does that mean that the point we've found is incorrect?
Yes. If the 3rd line is not concurrent with the other 2 lines, then this would mean that in drawing of any of these lines, at least one of these lines, we made a mistake. We might have made mistake in drawing both the lines. So that would warrant that the whole experiment be done from the very beginning once again. Bucho?
Yes, sir.
Good. So that's the experiment for the lamina experiment. Any other question? If you have gone, this is basically the same as number of steps that they've shown us over here in the procedure, and I have pretty much said the same thing, only in my personal words. So this is the primary thing, and we actually I did not mention over here that we should about the 3rd line, but I did talk about the 3rd line right now. I did talk about the precautions as well, that the holes must be quite small, so they do not affect the mass of the lamina too much, and also the lamina should be allowed to hang freely about the point of suspension. Point of suspension means in this case the pin, so it should not be touching the string, it should not be touching the clamp, it shouldn't be having additional source of friction under any case. Acha, one other thing that I would like to discuss, which I just skipped halfway, is that I told you that these 2 points has to be quite far apart from each other. They shouldn't be really close to each other. Let me show you why that is. I can use my regular paint for this thing. Ideally speaking, geometric lines are said to be shapes which have lengths but 0 thickness. So they only have lengths. Lines are not supposed to have width by definition. But in our worldly world, we cannot draw lines which do not have thickness. You draw with a pencil, no matter how sharp it is, it will have some thickness, because without thickness, you cannot see it. You cannot even work with it. So you have to first appreciate the idea that whatever lines that we draw, no matter how much sharp of a pencil that we use, lines will always have some thickness. That's the first thing I need you to appreciate. It's important. The second thing that I need to understand, let's say I'm going to highly magnify this thing, and that's why I'm choosing a very thick line just to make my point. Whenever you are drawing, if you have 2 lines which are pretty close to each other, finding out their exact cross point can be quite difficult by observing by your regular eye. For example, here I can see that this is the location. Let me draw with black right now. This is the location where the white space gets off, and this is the location where the white space gets off. So this whole part is my drawn line overlap. So my midpoint could be anywhere in between. Finding out the exact position of the midpoint over here by regular eye, whenever you're drawing with your ruler and pencil, can prove to be really difficult. Now you might tell me, sir, I'm going to choose the thinnest part of this whole intersection. That's essentially what you should do if you ever run into this kind of problem. It's unavoidable. but doing this is just an unwarranted or unrequired trouble that you can easily avoid. On the other hand, if we have two lines which have a pretty large angle between them, let me draw with the same color, maybe brown. So let's say this is one line, and let's say you have another line like this. If you have two lines with significant angle between them, finding out the cross point is a piece of cake. You can very easily say this is their cross point. You don't have to bother to go ahead to observe and compare and measure where the crossing actually happened. So finding out that cross point is actually much too simpler. This is why it is recommended that we should do this experiment with the holes not too close from each other. So having two holes, any of these two holes should not be really close to each other. They don't essentially have to be exactly 120 degree apart if I divide 360 by 3, but they have to be really far apart from each other. That's pretty important. Does this idea make sense about the difficulty of choosing the midpoint of the crossing point if the lines are because of the thickness of the lines? এটা বুঝা গেছে যে কেন এই পয়েন্টগুলো কাছাকাছি হওয়া যাবে না? বলবান?
Yes, sir.
That's one response. বাকিরা মনে হয় বুঝে নাই।
বুঝেছি স্যার।
আচ্ছা, I hope it did make sense. বইতে এর পরের পেজে আরেকটা ফিগার আছে, যে ফিগারটা আমাদের অ্যাকচুয়ালি নোটসে নাই because these are available in the book, so I did not make the kids write this thing. Have a look at on the next page, page number 73, this blue rectangle where we have a triangular object which is about to become stable by resting on its surfaces. So we have three types of equilibrium. The first thing that we call is what we call a stable equilibrium. Stable equilibrium means that you have the object resting on a certain surface, then you have rotated or tilted the object to a certain amount, but still if you now remove this force, try to understand this thing. Have a look at the first set of figure 5.21. There are two triangles. You can see over here that this is a sharp triangle which is currently, the left triangle is perfectly stable, no hassle there. The right triangle is made to rotate a bit on the right side, so it was pushed from the left to the right, and it did underwent a little bit of rotation. But if we now remove the force from this position, this object can automatically come back to its original position because the center of gravity is still on the left side of the R point. R in this case represents actually the reaction force, which is basically the pivot point for this rotation. This corner C is the working as a pivot point. So now anti-clockwise moment is gonna make the object come back to its original orientation. So this is what we're calling stable equilibrium. Stable equilibrium means that the object can come back to its original shape up to a certain limit. We can have unstable equilibrium. It means if the object starts to rotate, it's simply gonna fall over. This is the case for figure 5.22. On the left side of figure 5.22, this upside down triangle, we're gonna call this a stable situation as well, if this situation can persist itself. But the question is, will this situation persist itself on its own? If you hang up a triangular object on its vertex and balance it in this manner, will it be like this on its own for a really long time? The answer is a solid no. It will naturally fall over to one side, and whenever it falls onto one side, it is simply going to experience bigger and bigger moment because the G or the weight action line is gonna get further and further away from the ground touching point. So your perpendicular distance will slowly increase, and this object is definitely gonna fall onto the right side. There is no way this object can automatically come back to its original orientation, which is possible for the top two figures, which we call the stable equilibrium, and this is what we're calling the unstable equilibrium. The third point is what we have is neutral equilibrium. Neutral equilibrium is basically the case where it is actually pretty difficult to topple an object or roll an object. For example, if I give you a bit of an example, okay, consider this federal book. Close this book altogether and have it in your hand. You'll see that this book has three dimensions: length, the longest dimension; width, the second dimension; and then the height, which is the thickness of the book. You can basically place this book in three different orientation on a flat surface, on your table maybe. If you place the book with the width section touching the table, which means the book is standing vertically, you can see the physics writing in front of you. This is a case of this is one type of orientation where the book is, let's say, somewhat stable. With very careful alignment, you might be able to keep the book in this orientation for quite some time, but it will not be stable in this position for a very long time because it will have the tendency to fall back or forward. Now, these have a certain amount of stability, but it is not very stable. So I might as well call it unstable equilibrium. Now, and also, if you now place the book onto the long side, which is the binded side, the thin part where the name of the book and the second edition and the publisher's name are written. If you place it onto that side, the book is also going to fall back and forth. However, if you place this book onto its flat side, the typical way that we keep books on table, if you place the book on this side, there is no possibility this book is going to fall over onto any of the side. Naturally, this book is not going to rise up and eventually stand up on one of its side. Is it gonna? বুঝছো কি বলতেছে? If you keep the book on its flat surface, it's gonna stay like this for the foreseeable future. This is what we call the কি জানো third situation নাম জানো কি ছিল ভুলে গেছি. What is the name of the third situation?
Neutral equilibrium.
Neutral equilibrium. Exactly. This is the situation for that we call for neutral equilibrium. Neutral equilibrium means that this equilibrium will hold itself or maintain itself without any external help for the foreseeable future. That's basically about the equilibrium parts. Then we have this idea for hanging versus placing. I just discussed about this. Achha, we actually had this figure. Oh, okay, anyway, you have these figures over here. This actually makes sense. Beautiful. I forgot that we had these figures. But see, have a look at these figures. I think they make quite good sense. Then we have the part for stability. Stability basic idea হচ্ছে have a read. Let's have a read, and then I'm going to explain with the help of figure. It refers to how much force is necessary to topple over an object. Bigger force requirement means more stable and vice versa. It means if an object is at some orientation and if you want to topple over the object, it means if you want to change the orientation of the object about a certain corner or certain side, if you want to roll the object over, how much force are you going to need? If you need less force, object is less stable. If you need more force, the object is more stable, and vice versa. So to topple over the object, force must be applied to produce a moment that is bigger than the moment produced by weight. And to produce this moment with the smallest force, we must apply the force on the topmost position, that is farthest from the base. Let me explain what it means. Take a good look at this figure. I'm going to zoom on this one. Take a good look at this figure. There are a lot of labeling over here, but I want you to understand. This is a rectangular object. This corner, this bottom corner of this rectangular object is named as P, which is going to work as our pivot point. We want to roll this object clockwise onto right side. So we want this object to make a 90-degree rotation, and eventually this side should fall onto the ground. That's what we are trying to achieve. Now, whenever we are going to push this object over here, if this object starts to rotate about this point, the weight is going to produce an anti-clockwise moment because the weight is going to try to keep the object in its own position. To make sure that the object does undergo this rotation of toppling over, we have to produce a moment that is somewhat bigger than the moment that this weight can produce. So weight যতটুকু moment produce করতে পারবে, আমাদের applied force এর moment তার থেকে কিছু হলেও বেশি হইতে হবে for us to be able to make the object go complete its rotation. This is the important bit. I'll tell you, Asif. Yeah, I'll tell you how Asif just asked a question that how tall buildings are so stable. I'll tell you how tall buildings are made to be stable. I'll tell you this in a bit. So this is what we want to have. Now, to be able to make this thing, the amount of anti-clockwise moment produced by this W, anti-clockwise moment is going to be produced W. I can copy this picture and I can try to work with it. Maybe Word. Oh, beautiful. Big picture. So here, let me use a different color. About this point, the weight is producing an anti-clockwise moment, and using this force is trying to produce a clockwise moment like this. So to to make sure that the object starts to rotate, the clockwise movement produced by this F force has to be somewhat bigger than the anti-clockwise movement produced by the weight. So the anti-clockwise movement is actually W into B by 2. B by 2 means half of the base. That's why we use B by 2. So B would mean the total base length, the entire length of the base, and half means half. And the reason we are trying to apply the F force over at exactly on the top surface, because you have to understand that to start the rotation, we first have to balance the two forces. So if I just write that W into B by 2 should be initially equal into F into H. So if you want to make this rotation of the object possible by the smallest amount of force, by the least amount of effort, H has to be as big as possible, because a bigger value of H would enable you to have a small value of F, because the product has to be nearly equal to the multiplication of these two things. So to achieve that, we have to apply the force as far as away possible from the ground, so that we can have the highest amount of force, highest amount of moment possible by the application of smallest amount of force. And this is what we say for the condition for stability. So this equation is condition for stability. We might as well need this for some calculation, which I'll show you whenever some worksheet problem presents itself. Don't worry. The next thing I want to understand is that if we are having an object on an inclined plane, আচ্ছা এই inclined plane এর কনসেপ্ট আগে তোমাদেরকে বলি যে this is a idea for inclined plane. These figures were initially intentionally drawn in this pattern so that it would make better sense. But how did this figure come into existence? আমি ওই পার্টটুকু আগে তোমাদেরকে আলাপ করতেছি। So let's consider this thing. Let's say we have in here hinged surface. Hinged surface means, let's say this is ground, regular ground, and over here we have a hinge, and this hinge is attached with a plank which is resting on the ground. This is attached with a plank which is resting on the ground. Now, what I want you to understand, that this is the plank that we can lift up by lifting up this side. For experiment, we have placed a piece of rectangular block. Let me draw that with maybe brown, dark brown. We have placed a block right over here. What is this color called? Is this color maroon? No, it's dark red. Oh, my bad. So dark red. So let's say we have placed a block over here. For the sake of easier understanding, let me make that block a bit taller than its wide. It's gonna make our observation a bit more understanding. One thing that I want all of you to understand: the friction between the bottom of the block and this blue surface, this surface which we're gonna lift up about this point. So we can apply some force over here and we can start lifting up. The friction over between in this surface is so strong that whenever we're gonna start lift up, this object is not gonna roll over. Consider this fact, that this object is not gonna slide off. If the friction is too less, whenever we're gonna lift it up, this is definitely gonna start to slide down. But consider my words, that we have made sure that the friction is big good enough that this object is not going to slide down. So the only thing that it could do is roll over. So when or at which condition of this plank's orientation is this object gonna roll over? So this is a representation of this thing. Let's say this is the base of the whole object, and this is the center of gravity of the object, and in this case the weight is working vertically downwards. But for this figure, this weight line, this force is passing within the baseline, going through the baseline. If this is the case, then we're gonna say the object is stable. As long as the weight works through the base of the object, irrespective of orientation, the object would be stable. The object is not gonna roll over. If we keep on increasing this angle, and there will come a certain point, I mean, think about it. as we are gonna lift it up more and more, lift this up more and more, this object is gonna become more and more vertical, so the weight is gonna become pushed to the right corner. So here comes this figure. A figure একটা part important সেটা হচ্ছে for those who have fluid, I would like you to correct this figure on your notes a little bit. এই লাইনটা না হবে না, এই যে এই লাইনটা হবে না, এই যে এই লাইনটা হবে না. There are two lines over here. Only the line through which the weight passes through, that line should be there. মরণ, আমি আঁকতে পারি না ভালো. এই যে এই লাইনটা থাকবে, অন্য লাইনটা পারলে ফ্লুইড দিয়ে মুছে ফেলো. So there will come a certain point, if we keep on lifting up this plank, there will come a certain point where the weight of the object is going to pass through the exact bottom corner of the rectangular block. This is going to happen. This is unavoidable. This will happen. This is the case that we define as critical equilibrium. Critical equilibrium means it is on the verge to topple over, and it is the last end point of stability. মানে জিনিসটা হচ্ছে এরকম যে how can I put this, মনে করো তোমরা তোমরা কি থার্মাল কিছু হলো তো পড়ছো? হ্যাঁ পড়ছো, তোমরা ক্লাস 8 a 7 এ পড়ছো. The melting temperature of ice is 0 degrees Celsius, right?
Yes.
Do you know this? Yes. And also the freezing temperature of water is also 0 degrees Celsius. So 0 degrees Celsius temperature is basically the transition point of these two states. So you cannot say that at 0 degrees Celsius water is only ice, H2 is only ice. You cannot also say at 0 degrees Celsius water is only water. It could be at both. This is the temperature which is the boundary line of the two states. Below 0 everything is ice, above 0 up to 100, on above 0 you have liquid water. So why am I bringing this up? To give you an idea of borderline value, that in this case this is the exact alignment or orientation of the object which we are defining to be the last end point of the equilibrium and about to be the starting point of inequilibrium. So this is the situation that we call critical equilibrium, that the object is about to topple over or the object is marginally stable. These are the terms that are used in the question. I'll say it again. The object is about to topple over, or we say the object is at marginal equilibrium or critical equilibrium. So in this case the object is still in equilibrium, but it is very very likely to move away from the ground. So it is about to start rolling. এখনই উল্টায় পড়বে. And then comes the next possible scenario, that if any object is in such an orientation that the weight working line goes outside the base. So you can see over here for this third figure, the student actually did rub of this figure that weight is outside base. So this is the baseline. I mean, this part of the length is the baseline. I mean, from here through here, this is the baseline, and the weight is falling out of the baseline. If that happens, then the object is said to be unstable. In this case, the object will definitely fall over. So basic idea that if you somehow manage to bring up an object in this orientation by applying, by let's say we're gonna hold the object on top of this surface with our hands and achieve at this angle, and then if we are leave our hand, the object is gonna start rolling down. So that's the idea for stability. So important bit, the summary of the whole discussion is that we have to find out, by extending the weight line starting from the center of gravity vertically downwards, does the weight line goes to the baseline or not. If it does go through a baseline, it is good stable, or we can say it stable. If it goes exactly on the corner of the baseline, it is critical stable or critical equilibrium, which means it is about to topple over. If that weight line falls out of the baseline, then this object is perfectly unstable and it's simply going to roll over. So that's the three different definition that we have. So we might as well take a bit of a read over here. আচ্ছা, তোমরা একটা কাজ করো, বলবান স্টেবিলিটি শুরু থেকে এই পেজটা পুরোটা একবার পড়ো সবাই। তোমাদের কাছে নোটস আছে, read this entire page. I'll give you 2 minutes and then I'll resume lecture. Any question about these parts? Anything?
না স্যার নাই।
আচ্ছা, এরপর আমাদের এখানে কিছু টেকনিক্যাল কোশ্চেন আছে। এই কোশ্চেনগুলো আমরা দেখতে পারি। Is a pretty simple stuff that we have talked about. And then there is a question over here. This is a pretty interesting question that I'd say. এই কোশ্চেনটা অ্যাকচুয়ালি হচ্ছে আগের বইয়ের। তোমাদের কারো কাছে লো প্রাইস এডিশন বুকটা আছে? তোমরা কেউ কোনো সময় দেখছো বা কিনছো? লাল কাভারের
কোনটা
একটা
স্যার?
ক্যামব্রিজ লো প্রাইস এডিশন একটা বুক আছে, which looks something like this. এই যে এরকম উপরে যেখানে ক্যামব্রিজ লো প্রাইস এডিশন লেখা থাকে। এনিওয়ে,
No.
আচ্ছা ঠিক আছে। This question is from that book, which was the earlier book from Cambridge Andrews book. This is a pretty interesting question. I'll walk you through this question. I want you guys to understand this figure. I'm gonna copy this figure in my paint to make this math a bit more understandable. But have a look what is being shown here. There is a plank. A person is standing on the plank, and we have some information given to us. Plank AB of mass 12 kg is supported by two triangular stands, A and B. A and B. Object P has a mass of 2 kg. There is an object P which is a mass of 2 kg. Person A has a mass of 52 kg. It was information. And then we have some dimensions given. From the very left of the plank to the position of object P, this is 0.5 meter. From the P object up to the support point A, this is also 0.5 meter. Let me zoom in so you should be able to see the 5 a bit more clearly. Meter is not written because the space was a bit less. Okay. Then from this point all the way up to the position of the person. Nah, position of the person kotha lebe karon na. So A point theke from the support point A all the way up to support point B. All the way up to support point B, the length is 2 meter. And on the right side, outside support point B, the remaining length of the plank is 1 meter. So the total length of the total length of the plank is how much? Have a count. How long is the plank altogether?
4.
4 what?
3.5.
How do you get 3.5?
4 meter.
0.5, 0.5 to 1.
Oh, yes.
4 meter, exactly. You have to say the unit as well. How long is the plank? 4 meter. You have to say the meter as well. So the plank is 4 meter long, and the person is located, the position of the person is labeled by this information, that from the support point B, on the left of support point B, the person is 0.4 meter on the left. Now, this student who copied this figure actually placed the person, labeled the person pretty much at the center between them. But as it happens, the length of this entire plank, entire length is how much? 2 meter. This person is only 0.4 meter away on the side, which means he's definitely not on the middle. He's really close to the B side. ঠিক না? Try to think. Here is 2 meter and his distance is from B is how much? 0.4. So he's closer to which plank?
B.
Obviously he's closer to plank B. So this figure is not drawn to scale. I'm going to try to draw the scale with a bit more redraw the figure with a bit more sense. So this is the information that we have available. Then comes this rough writing, which were I think were written by pencil, so that the student could understand what these things are. The question says label the reaction forces on the plank by support A and support B as RA and RB respectively. So reaction forces means the weight of the plank, the weight of the person, the weight of the object P, all of them are going to work downwards. And as a reaction by Newton's third law, the planks are going to apply some force on the upward direction. So we had to draw vertically upward forces. In this case, they are labeled as RA and RB. Although the length of these two arrows are drawn to be equal, but we have to assume that they are not essentially equally forced, because once again, I have to mention this figure is not drawn to scale. So first of all, we are done that, and then the question says find RA and RB. So we have to find out the value of these two forces. So how can we find out this value of two forces? This is the primary discussion that I'm going to take you in. Then it further says how far can the person move safely before the plank starts tilting. This is pretty interesting. So এখানে একটা জিনিস একটু বাদ পড়ছে, সেটা হচ্ছে how far the person can move safely on the right. On the right টা বলা হয় নাই. I should have said to the right. So he's here now. So if he starts to walk slowly to the right, maximum how far can he move before the whole plank starts to tilt? Now, why this thing should start to tilt, I'm going to discuss this in a bit. But let me redraw this whole figure for a bit of easier discussion, and we can start doing the math. I'm going to show you how to do the math step by step, pretty much like the way I do for every class, so that you don't have to necessarily take this information randomly. I'm going to explain this to you, then you can read through the working, and it will be easily, it should make better sense to you in that manner, I hope. I cannot select the whole picture. Select two pictures. I cannot select two pictures at once. Acha, never mind. I don't have to copy the picture. Might as well try to draw the picture anyway. So I'm going to put zoom in, zoom out to 100%. So I'm participant list close করে দিয়েছি. If you have any question, please voice up.
না স্যার নাই।
Now, anyone, if you have any question, voice up so that I can hear that what you are about to say. You see the figure in your question, and you tell me the dimensions if I mistake at any point. Let's say this is our plank, big enough plank, and we're going to require two supports, so might as well draw two supports, one over here, 1 meter, okay, and one over here, over here. Okay, I think okay. All right, actually, I have to try it. Okay. And then we have one rectangular piece of object. Let me label that with maybe ash color. So this object is over here. No, rectangle. And then we need a person who is standing about, this is 2 meter, this is 1 meter, this is half meter, this is 0.4. So maybe the person is standing right up over here. This is what the person is standing. And I'm going to label the distances as well. So I might as well use a bit thinner line. I'm going to use dark for the distances. So this is 0.5 meter. This is 0.5 meter. So I might as well label the force over here since I'm at this point. This is RA. And this is RB. Oh, okay. And then this part is also 0.5 meter. From here to here it's 2 meter. And then from here to here is 1 meter. এই পর্যন্ত গেল, and we are going to have to label two forces as well. Might as well label those two forces. So we have two weights of this object. This was definitely defined by 2 kg object, so the weight over here is 20 Newton because W equals to mg, and the weight of the person, which was vertically down, thinner line, and this force is 520 Newton because he was defined as 52 kg. It's pretty less for a grown-up person. Anyway, and this distance is 0.4 meter. দেখো সবকিছু লেবেল করা হয়েছে না? বাদ পড়ছে কিছু? I think if we want, we can also want to label the two support systems A and B. I think that's pretty much it. So let's go ahead and try to find out how can we calculate the values of RA and RB. Now here's the deal. There are two different ways we can approach this problem. We can either go for simultaneous solution or we can go for singular solution and then replacement. We're gonna use, because the whole setup for this position of the object and the person and the plank and the supports A and B, this thing is in equilibrium, which means it is in equilibrium for force. It is also in equilibrium for moment. So the first thing first is that we're gonna write up the equation for this whole problem in terms of force. So obviously upward forces should be equal to downward forces. So if I go ahead for this one, here the two upward forces is RA plus RB, and here we have 3 downward forces. What are those downward forces? 20. Do our plank have any weight? Yes. I forgot to label the weight of the plank. The weight of the plank should be labeled at the middle. That should be 120 Newton, because the plank was said to be 12 kg. এটা বুঝছো কি সবাই পোলাপান? এটা কোথা থেকে আসছে?
Yes, sir.
দেখো না বুঝলে জিজ্ঞেস করো আমাকে। So the total upward forces equals to total downward forces, 20 plus 120 plus 520. So this gives us our first equation, RA plus RB equals to এখানে হবে 6 and then 3 2s are 6, 660 Newton. Equation number 1 সেটা পাইলাম। নেক্সট আমাদেরকে, এটা হচ্ছে আমাদের ইকুইলিব্রিয়াম অফ ফোর্সের ইকুয়েশন। নেক্সট আমাদের কাজ করতে হচ্ছে ইকুইলিব্রিয়াম অফ মোমেন্টের ইকুয়েশন দিয়ে। ইকুইলিব্রিয়াম অফ মোমেন্টের ইকুয়েশন নিয়ে যখন আমরা কাজ করব, so we have to choose here in this question. No point is defined as a pivot point, because this was a stable situation and nothing is rotated or anything. The question doesn't specify any specific direction of rotation. It doesn't. So we can choose. In this case, we have the privilege to choose which point do we want to take as pivot, which gives us an enormous advantage if you are smart. I'm going to show you 2 different ways to do the math, and then you can choose what you should do. The first thing is that I can try take my moments. Let's say I'm going to take my moments for the first consideration about the left point. I'm going to take moment about this point. Let me name this point. Let's say this point is X. So taking moments about point X, you have to write this in your question. If you're solving this kind of problem and you have to label some point that you need to define, label that point on the figure. You can do that, and then you can write taking moments about X. So আমরা যদি X point থেকে moment নেই, তাহলে simply হচ্ছে আমাদের clockwise moment হবে কিছু, anti-clockwise moment হবে কিছু. So we're gonna start working with that. To show you how the moments are gonna work out, I'm gonna copy this picture so that I do not mess up the original picture, so that I can use it for the next discussion as well. So I might as well. Why can't I? Okay, I'm keeping this in the memory of the PC, saving it elsewhere, and let's mess up this figure right now for our drawing. So if I consider this as my pivot point, taking moment about this X point, I want you to visualize all these curved lines that I'm about to draw. You don't have to draw them, but I'm just drawing them over here to help you visualize how the moments are going to be. If you consider the forces one at a time, if this is a pivot point for this plank, and this is the only weight working on this plank, this will produce a clockwise moment. If this is the only upward force, this will produce an anti-clockwise moment, clockwise moment, clockwise moment, and anti-clockwise moment. So we're going to have 2 anti-clockwise moments, and we're going to have 3 clockwise moments. দেখো এই ফিগারটা বুঝা যাচ্ছে কিনা? I'm just trying to show you what will be the duration of the moments about this point if we consider this point as a pivot point. You might wonder, or you might wonder that, sir, no point is actually defined here. On which basis did you choose this point? The answer is no true basis. I had the opportunity / independence / privilege to choose any point. I chose a point. So I chose a point exited from the left. I could have chosen any point on this figure, and this would just work out fine. So I chose this one. There is no hard and fast rule which point you do have to choose. For example, I chose this point. Now, if I start writing up the moments, so all the anti-clockwise moments I'm going to write first. So let's say this is the force. This is RA. How much I don't know. The distance of RA from X is how much? From the X to RA, how much is the distance? Someone respond.
1 meter.
It's 1 meter. This is RA into. I'm going to write 1.0 because I don't want to show the addition. You might also want to show, if you want, you can show that addition, no big deal. plus RB into how far is X all the way to RB? This is 3 meter. 3 na?
3.
3. This should be equals to the clockwise movement. So this is 20 multiplied by 0.5 plus 120. এই যে এখানে আমাদের কিছু হিসাব করার ব্যাপার আছে কারণ আমি এই 120 যে ফোর্সটা এটা কোনো লেংথ ইনফরমেশন লেভেল করি নাই নাও the question did not say it's an uniform plank but the question also did not say it's a non-uniform plank. If nothing is mentioned about a plank, we naturally assume it to be uniform plank. Uniform plank মানে হচ্ছে the entire length of the whole plank is 4 meter, so the mass or weight of the plank should be working exactly at the middle, which means this should be labeled, this point is the half midpoint of the whole length, which means on the left side we should have 2 meter, on the right side we should have 2 meter. This essentially means this much length should be how much? 1 meter, nanometer হয়ে গেছে 1 meter, and this much length should also be how much from the force? এটুকু কত হবে?
1 meter.
1 meter. এটা কি বুঝছো সবাই বলবান? Considering the plank as the midpoint, this is the 14 working.
জি স্যার।
So এখন টোটাল ডিসটেন্সটা কত আসবে? x থেকে এই টোটাল ডিসটেন্স আসবে হচ্ছে 1 plus 1 2.0 plus 520 into কত হবে? এটা একটু হিসাব করে বলো। x পয়েন্ট থেকে 520 টোটাল ডিসটেন্স কত হবে? I'm gonna write in this format.
2.6 meters.
It's gonna be
0.6.
but I prefer to write in this format just to show you that what I'm trying to achieve. I consider the whole length, then I subtracted the part that is close. So এই ইকুয়েশনটা ট্রু হবে। এখন এই ইকুয়েশনটাকে যদি আমি একটু প্রসেস করি I can get a equation. So this is going to be RA plus 3RB. My handwriting. 3RB equals to এটা হিসাব করে দেখো তো কত হয় ক্যালকুলেটরে। At least 2 or 3 people confirm me the same value. I'm deciding to be lazy not to use my calculator. এটা কত আসে দেখো তো।
$1,602.
Someone else confirm?
I get the same.
Good. So we have two equations over here, and now we can simultaneously solve them to find out the value of RA and RB. So এটা হচ্ছে একটা process. এটা বুঝছো কি সবাই? You can simultaneously solve these two equations. I am not willing to show you that. You guys do know how to solve simultaneous equations, right? Yes, I'll take it as a yes. There is an alternative way. Other than choosing any random point on this equation, have a look. Here we had two unknowns RA and RB. What if we choose one of these points, either this one, let me use a different color, either this point, if we choose this point as my pivot point, what will be the moment of RA about this point? RA goes to this point. If a force goes to a certain point and that point is considered as a pivot point, what is the moment of that force about that point?
Zero.
The answer is correct. This force about this point produces a zero moment because the perpendicular distance is zero. Because the force does exist, but there is no distance because this force is practically going through this point. So essentially, the moment of RA about this point would be zero. Similarly, the moment of RB about this point should be zero. So if I choose any of these 2 points, either this one or this one, as my pivot point, because I could choose my pivot point, from this equation, one of the variable would directly disappear. This is why I actually saved this figure so that I could mess up this figure right now. So I'm gonna take this figure up and I'm gonna show you this alternate calculation which I am trying to describe. So in this case, I'm gonna rub off this X point. Let's say, let me rub off this X point. And let's say I'm gonna give another point. Let's say I'm gonna take moments about this point, calling this point P. Now I'm gonna write taking moments. I have a reason to show you two different calculations so that you can choose and compare and understand what's the advantage of one over another. Taking moment about P. আমি যদি এখন P থেকে moment নেই, now I would like to first draw the moment directions. This will produce an anti-clockwise moment. This does not produce any moment. This will produce a clockwise moment, anti-clockwise moment. So I have two anti-clockwise moment, this and this. I have two clockwise moment, these two. So taking moments about point P. So this would be 20 into 0.5 plus RB into 2.0 should be equals to 120 into 1 plus a bit more space 520 into 2 minus 0.4. দেখো এই কোশ্চেনটা ঠিক আছে কিনা? দেখো এই কোশ্চেনটা ঠিক আছে কিনা? If you have question about this equation, ask me.
আসলে নাই।
এখন আমি সলভ করলে কিন্তু আমার ইকুয়েশনে কিন্তু একটাই ভ্যারিয়েবল। এই ইকুয়েশনটা সলভ করে দেখো RB ভ্যালু কত আসে। Do your own calculation, write this up and give me a value for RB. There will be multiple steps over here, so I'm giving dotted lines and give me a value for RB. At least two people confirm this number. কত আসছে?
So 471 আসছে আমার।
Okay, 471 for
471.
471.
Okay. So 471 Newton. So once you get 471 Newton, you can directly replace this number over here and you can find the value of RA, which reduces your mathematical effort. ঠিক না? এই আমরা যদি একটা unknown ফোর্সের পজিশনটাকে যদি পিভট পয়েন্ট হিসেবে চুজ করতে পারি, if the math question allows us and if we do that, this automatically gives us the other unknown, which helps us to find out the original unknown much too easily. So if I take moment about either this point or this point, we can find out the other force really easily. যদি আমরা যে কোনো একটা র্যান্ডম পয়েন্টের এগেইনস্টে নিছি, যেখানে যে এই লেফট এজে নিছিলাম, তখন আমাদের দুইটা সাইমালটেনিয়াস ইকুয়েশন আছে, এখন আমরা দুইটা সাইমালটেনিয়াস ইকুয়েশন সলভ করাবে। I'm not saying it's difficult to solve two simultaneous equation because you can simply get over here that you can replace the RB in terms of some subtraction format and it will come out immediately after maybe 2 or 3 lines. But using this process, RA can be altogether obliterated or given out or taken out from the equation by virtue of what we chose to do. দুইভাবেই করা যায়। এই পর্যন্ত বুঝা গেছে কি সবার?
জি স্যার।
এখন তোমাদের অ্যাকচুয়াল এক্সামে তুমি যে কোনো ভাবে করতে পারো, যেটা তোমার কাছে ইজিয়ার মনে হয় তুমি সেভাবে করবা। নট এসেনশিয়ালি টাইম বাঁচানোর জন্য আমাকে নিচেরটাই করা লাগবে ব্যাপারটা এরকম। যদি এরকম হয় যে নিচেরটা করার জন্য তোমাকে যে লেন্থ কনসিডারেশন করতে হচ্ছে সেগুলো তোমার কাছে ঝামেলা মনে হচ্ছে বা কমপ্লিকেটেড মনে হচ্ছে, ইউ গো ফর দ্য ফার্স্ট ওয়ান, বি মাই গেস্ট, নো প্রবলেম। বোথ অফ দেম আর ইকুয়ালি অ্যাকসেপ্টেবল এন্ড ইকুয়ালি মার্কস স্কোরিং। একটাতে লেখা একটু কম, একটাতে লেখা একটু বেশি। যেটা তোমার কাছে ইজিয়ার মনে হয় তুমি ওটা করবা। ডু আই মেক সেন্স?
জি স্যার।
আচ্ছা, থার্ড যে কোশ্চেনটা ছিল, থার্ড কোশ্চেন আমরা ইনশাআল্লাহ নেক্সট ক্লাসে পিক আপ করব বিকজ অলরেডি 4 minutes past 7:30 and I'm stopping the lecture right now and we'll resume lecture inshallah next class. Thank you very much. Allah Hafiz.
আসসালামু আলাইকুম স্যার।